2 lessons are a lot of definitions. Let's get things going. So, the first thing is to realize that we're going to start doing all of our trig on Cartesian planes. Oh, this is coordinate planes. Same thing as Cartesian. Spell. That's the best I'll try. A Cartesian plane or a coordinate plane means like an XY axis, right? Like just a basic graph. So we're going to be putting almost all of our trig to start this semester on graphs like this. XY axis, you guys know all that standard stuff. And we're going to have some set definitions for those Cartesian planes. Okay, to start things off, we're going to talk about the positive x-axis. So when you hear or read anything that says the positive x-axis, they're talking about this portion of a Cartesian plane. That's the positive side of the x-axis. Anything over here would be the negative x-axis. You're also going to need to know the word counterclockwise. So everything that we measure today will be counterclockwise from the positive x-axis. So that means we're going to be measuring things in that direction. Make sense? It gives us a nice good standard. In fact, they call it standard position. Yeah, that's nice and easy. So anytime an angle is measured from the positive x-axis counterclockwise, you're talking about standard position. What you'll be measuring is an angle between the positive x-axis and some line. I'll draw that line. The next page has a better graph with it, stuff like that. That line is called a terminal arm. And the end of that line is called a terminal point. So, if you have a terminal arm, the measure of the angle in standard position is from the x-axis to the terminal arm. That's called standard position. I said we're going to learn a lot of definitions, right? So terminal arm, terminal point, standard position are the 3 that should all be brand new to you. Terminal arm is just a line somewhere on a graph. Terminal point is the end of that line. Standard position is the angle between the x-axis and that line. There's 2 examples down here on the bottom. If you were to label the standard position angle, it would be right here. That'd be standard position, SP. This thing would be the terminal arm, TA. This point would be the terminal point. That makes sense? Pretty basic. We need to all be on the same page at all times with definitions, or else this unit gets crazy. So if you have a question about a definition, just ask. All right, for the next one, we're going to try it again. So the standard position angle is from the positive x-axis counterclockwise to the terminal arm. That would be the standard position angle. So that angle is actually bigger than 90, right? Still standard position if it's bigger than 90. Notice that we're always going counterclockwise from the positive x-axis. Yeah.
So it could go all the way to...
It could go all the way around to 360 and bring it right back there. This thing right here in green is called the terminal arm. The end of that terminal arm, we call that a terminal point. You're not going to be able to label it, but you're going to be able to use it in a sentence. So if I'm like, the terminal arm is at an angle of 63, you need to know, okay, there's a line from this measure on the graph. That make sense? Yeah. All right, the next slide kind of breaks down a few more, but it shows you a good example of it. Yeah, you.
Will the terminal arm always come from origin?
Yeah, so like the terminal arm, when we're measuring it in standard position, always starts like this and goes that way. We call that Oh, there's a name for it. The terminal arm, sometimes it's called the initial arm because it starts here and then moves somewhere else. So this positive x-axis, they call it the initial arm. It's like where it started. Oh yeah, look, it said that. Positive x-axis is the initial arm. And then it moves to become the terminal arm. That's where it stops. That's why you measure the angle in that direction. Okay. Here's kind of all the definitions nice and laid out. We'll label them on here. Okay, there's also a couple of new ones towards the bottom. The first thing is a Cartesian plane. That's just an x-y axis. You should be nice and comfortable with those, I hope. The initial arm. So if you see the term initial arm, it's talking about the positive x-axis. Initial arm. The positive x-axis is always there, it never moves. The terminal arm is where that thing rotates. So right now, it's rotated out to here. We would call that the terminal arm. We're going to label the standard position angle in here, even though it doesn't have the definition on this side. The standard position angle is from the initial arm to the terminal arm. So that's the standard position angle. The standard position angle is in between, in between 0 and 360, because you could go from right here, which would be 0, rotate it all the way around, that would be 360. Make sense? That's kind of what Jackson had alluded to. All right, the next definition is called a coterminal angle. What does the word like co usually mean? So if you like played a sport and you had two people and they were co-captains, that means they're both captains, right? Both people. Yeah, they're both humans. Yeah, equal. Sorry, they're people. Yeah, they're people. They're equal people. Yeah, they're equal captains, right? They did the same. So if you're talking about co-angles, you're talking about two angles that are the same. They would take you to the same terminal arm. So this angle right here looks like, if we were to guess, maybe like 100, right? 90 would be straight up, a little bit further, so maybe like 100. Technically, we don't know how many times that terminal arm did a 360 before it got there. So you could imagine that this angle did something like this. I'll do it in black. It could have started here. It could have gone all the way around once. And then it could have gone the rest of the way. That would be a coterminal angle. It would be the same spot where it ends, but it actually did a full 360 plus the other 100. Yes?
So if the terminal arm was like, what's it called? The x-axis, like positive, where the 360 would be more.
They would have to define it somehow, but it'd be 0 or 360, but those would be coterminal angles. Because 0 gets you right here. 360 would get you right there. That's coterminal angles. Yeah.
How does that make sense in like the railroad, for example? Like, wouldn't it still be, like, you can go all around 100 times, but then if you end up at the same spot, wouldn't the angle between the terminal arm and the initial arm still be the same thing? Like,
Yeah. The standard position angle is the same. So you would measure it the same way, right? You would still say that's 100. But that angle technically was 360 plus another 100.
So the standard position angle is always just that, like, same, but the coterminal angle is something completely different?
Exactly. So the standard position angle stayed the same. The coterminal angle was something different. It was 360 plus that 100, which is what we're saying. So an example of coterminal angles could be 100 and 460. Because 100 gets me to this terminal arm, add another 360, so do a full circle, and that would get me to the same spot, but the angle's actually 460 degrees. Imagine degrees, that's just, a degree is just how much you're turning something, right? So like if I'm like standing straight forward and I say that's me at 0 degrees, and I turn 90 degrees, I'd be like that. What if I did 360 degrees plus another 90 degrees? Still looking the same way, right? That's the idea with coterminal angles. So me doing a full spin in the 90 is the same as me just doing 90. Right? It ends up at the same spot. Make sense? It's a little tricky. It's a little weird to comprehend sometimes. Reference angle. This is the one that really screws everybody up. A reference angle is the angle between the terminal arm and the x-axis that's closest to it. Okay, so the reference angle is between the terminal arm and the closest x-axis. That means if you were to look at our example right now, the terminal arm and the closest x-axis would be right here. It wouldn't be the standard position angle. Standard position angle is always the positive x-axis. The reference angle is the closest x-axis. So we would say that is the reference angle.
So if the terminal arm was at 90 degrees,
then you would just go standard position probably.
So standard position and reference angle could be the same thing.
They could be the same thing. So if your terminal arm is anywhere in quadrant 1, the closest x-axis would be the standard position angle. That make sense? Reference angles can be measured either way. So they don't have to go counterclockwise. They could go clockwise. What I mean is, if I took an angle, a terminal arm, and I put it here, the reference angle would be here. That would be the reference angle. Because that's the closest x-axis. That make sense?
You kind of always pick between the two, unless it's less, like, so you pick, it's both of them when, then? If you pick between the two?
If the reference angle, or sorry, the terminal arm is in quadrant 1, then the standard position angle and the reference angle are the same thing. Because the closest x-axis would always be going back to that positive arm. Yeah. This idea of always going to the closest x-axis can be explained in another way. It can be explained in that the reference angle is always in between 0 and 90. It will never be bigger than that. Reference angles are basically what you've always been calculating, right? Every triangle we've ever had has always been between 0 and 90 because we always said it was a 90-degree triangle, kind of like that. So this is what we're used to. 0 and 90 is just acute, but some people, oh no. Some people just forget that the word acute means in between 0 and 90. So you're going to have questions where they're going to draw a terminal arm, for instance this one right here, and they could ask you to calculate the standard position angle, which means you calculate this big angle. Or they could ask you to calculate the reference angle, which you would need to know is this angle. So that's why knowing the definitions is so important, because they could ask you for either one, and you're not going to know which one unless you know the definition.
Can you say that the standard position only goes 100, but that won't just be...
Exactly, yeah. Because that's the only way to get to the other side. Yeah. All right, the last definition that we're going to do is called general solution. We don't do a lot with general solution. General solution comes extremely in handy next year, especially if you go 30-1, go 30-2, it's completely irrelevant. General solution is a way of writing out all of your coterminal angles. So, for example, if we're saying that the standard position angle for this question was at 100 degrees, we found that a coterminal angle of it was 460 degrees. How did we get that 460 degrees? We added 360. Now, what if I just added another 360? Would I get to the same spot? I would. And what if I added another 360? I'd keep getting to the same spot. So your general solution to a question is the standard position angle plus 360 n times. Where n is an element of the whole number system. You couldn't have a decimal in there, or else you wouldn't be doing your whole 360. Okay? That is your general solution to any question. You take your standard position angle, you just keep doing circles however many times you feel you need to. That would cover every single possible coterminal angle. It would cover 1 circle, 2 circle, 3 circle, 4 circle, all the way up to infinity. How are we feeling about those? It's easy now when we're just reading them, right? In like a week, we'll be like, which angle? What are you talking about?
How do you define general solution?
Probably if I was to define it, I'd just take this. You could write a standard position plus 360n, and that's how you define it. But it's just it's a mathematical equation that shows all coterminal angles. Like that's the actual definition of it, I guess. N is like just a number you could pick. It's how many circles you want to do. If I want to spin around 3 times, then I'd say n equals 3. Right? So if I wanted to get to 460, then I would make n equal to 1. Because it'd be 1 times 360, that's 1 circle. If I wanted to do 2 circles, I'd go 2 times 360 plus 100. They would always be getting me back to that same spot. No, you just put n. Yeah. So like, a way you'd use that is I would say like, what's the standard position angle, and then what's the general solution to that standard position angle. And you would say it's that standard position plus 360n. And that would cover all the circles. We do very little general solution in this class. Okay, so don't stress too hard about it. It's applicable for next year mostly. Yeah.
So general solution n can equal anything from 4 numbers.
How would be a question? Anything? What do you mean?
You put the standard position angle into the equation, then it's right whenever level.
Yeah, I see what you're saying. Maybe when we start to see what a general solution question looks like, it might help. Well, we'll have to wait a little bit till we see that. Because I see what you're saying. You're kind of like, I could just do that number and figure out anything. It's just a way of showing all your solutions, I guess, without having to actually write out each single one. Again, I'm trying to think of how to explain it without getting too far into trig that you don't know yet. Remember how I kind of alluded yesterday that we're going to be doing circles? So you could picture that this terminal arm is there, but if you're on a big circle, then I could be doing rotations a whole bunch of times. So, for instance, you'll start getting questions in the future, not this year, where you're going to be taking things like Ferris wheels or tires on a car, which are rotating. And what they're actually doing is they're creating all these angles all the time. But a truck tire could rotate like 50 times, and then you're trying to figure out where it is on the 51st revolution. That's where a general solution could become useful. But again, that's so far beyond where we are, right? So don't be stressing about that. But that's why it might be useful when it becomes word problems. Again, next year stuff. Like that, those types of questions you won't even see this year.
I was going to say, how is there a terminal arm on a tire?
It's the radius.
Well,
I mean, picture like this is the center, so the terminal arm is the radius to the edge of the tire.
So you just like
It would be.
Oh, I guess it wouldn't really matter.
Yeah. Yeah, and anywhere on it, depending on what you're trying to do, right? So, for instance, like, just because this is way off topic, I'm gonna pause this. Back on topic. So those are all our definitions. We're gonna work with those definitions today, only in quadrant 1. Okay, so today we're only going to be in quadrant 1, which means our standard position and our reference angle will be the same thing all the time. Thursday, we're going to move the terminal arm into all quadrants, which makes things, that's when the definitions get a little trickier. So we'll review the definitions Thursday before we actually start getting into things, or at least talk about them as we're doing them. Today what we want to do is set up a couple formulas for us and learn a couple tricks. The first trick we've actually already done before. We did it in Math 10C, and we did it in our review yesterday with that Cartesian Plane question. And the trick was that everything's a triangle. So if everything's a triangle, you should be able to look at a terminal arm and draw a triangle, just like we did yesterday. That triangle goes like that, where we call that our y value and that our x value. It's a trick we already know, but it's super valuable. In this unit, there's going to be like tricks and stuff to get through things quickly, and there's going to be formulas to get through things quickly. At the end of the day, if you're ever completely lost, you can always resort back to these ideas. Going to a right-angled triangle and using Pythagorean theorem and the trig ratios, which is so controlled. You'll always be able to resort back to those things. But we're going to use those things to create a few formulas to make things a little bit easier. So the first thing is we're going to talk about something called R. R is a hypotenuse when you're talking about a Cartesian plane. The reason we call it R is because in the future we're going to have circles, and R is going to be your radius, which is kind of what we talked about, right? So that's why they call this thing R. But it's really just your hypotenuse on a right angle triangle. The first thing that we're going to do is use Pythagorean theorem to make a formula for R. Pythagorean theorem is just R squared equals x squared plus y squared. Right? If we look at that, that would make sense. If you wanted to actually get R in terms of x and y, that means you need to get R by itself. So I would need to do what to both sides? Square root it. So your formula is going to be R equals x squared plus y squared. And I'll be completely honest with you, I never use that formula ever, but I know a lot of people do. So if you're ever given a question and they're like, find the terminal arm, the measure of the terminal arm, or the measure of this line, you could just jump right to that solution, or you could do Pythagorean theorem from start to finish. That's what I do. Okay? Both get you the same answer. This is just a short form to figure out what R is. You will be given that formula. The next thing we're going to do is we're going to talk about the value of theta. If you look in this question, theta is your standard position angle. Right? Positive x-axis up to the terminal arm. That would be my standard position angle. They want you to write the value of theta in terms of x and y. To do that, we're going to use SOHCAHTOA, because that's how we connect side lengths with angles. So using SOHCAHTOA, that would make this the opposite, this the adjacent, and this the hypotenuse. To write theta in terms of x and y would mean that you use tan is equal to opposite over adjacent. So tan of theta equals y over x, which means that formula will be given to you, and I could always just say, what's the standard position angle? And you'd be like, tan of theta equals y over x, that's my answer, calculate it. Or you could always resort back to this and use SOHCAHTOA. Right? That's what I'm trying to get at. These things could always be connected. all the way back to the base roots of grade 10. The x-coordinate. So if I ever gave you something and I said, what's the x-coordinate of this? And you knew the angle and the radius. And I said, what's x? You would use SOHCAHTOA, right? You would use adjacent to hypotenuse, which would be cosine. And you would say the cosine of theta equals the adjacent over the hypotenuse, which is x over r. We take that basic idea of SOHCAHTOA and we rearrange it to get a formula for x values. To rearrange this for a formula of x values, you just multiply both sides by r. So this thing changes to become x equals r times cos of theta. That means that x values on a graph could be calculated using that formula. That formula will be provided for you. Or if you forget that formula, you go right back to basics. We just use SOHCAHTOA to find it. I'm not doing anything crazy here. You could probably do almost our whole trig unit, except for one lesson, with just SOHCAHTOA and Pythagorean theorem. It's kind of crazy, but it's true. Even at the 30-1 level, like, I can do almost every question with SOHCAHTOA, Pythagorean theorem. A lot of it. Yeah.
So these are just strategies like if you're lost, you sort of have these and they aren't given to us.
These are like quick ways through questions. So if I give you a question and you knew the radius, you knew the angle, I said, what's the value of x? You could jump right to this formula and calculate it. Be like, oh, x value must be this, because I know these things about it, right? Or if you were completely screwed up, you could draw a diagram, figure it out, and use SOHCAHTOA. So we're just using our base foundation to actually calculate it. The last one is the y-coordinate of p in terms of r and theta. Trying to figure out the y value, it's the same idea, except now it's using the sine ratio. Right? If I use SOHCAHTOA to find y, it would be opposite over hypotenuse, rearrange it, that's your fourth formula. I think those four formulas are all given to you. I should have written this one right too. Sorry, that one will also be given to you. So it's quick ways to link things together. The way that this looks. Here's a question, pretty standard question, pretty easy question. You could have definitely done this in grade 10. You'll probably see something like this even on a 20-1 test. It says the point P is at 4,7. It's on the terminal arm of an angle theta in standard position. Point P, 4,7. So we're up there. That's my terminal arm. I'm going to call it R. The angle theta is in standard position. That tells you where to draw your angle on your diagram. What does standard position mean? Positive x-axis, counterclockwise. That's theta. Ready? But see how you need to know that definition? Because what if this was somewhere else and I use a different term, like reference angle? Then you would need to know where to draw theta. This theta goes here because it says standard position, and that's how we measure standard position. Now we can draw the rest of our triangle. That means this should be x, this should be y. Those values of x and y we actually know. What's x? Yeah, sorry. And what's that one? 7. There we go. That's exactly like what we just did in grade 10. Like, almost identical to the question we did the other day. Determine the distance from the origin to P. Or they could say determine the distance to R. You could use Pythagorean theorem, or you could use our new formula, which was R equals the square root of 4 squared plus 7 squared. Okay, so that's what I mean when I'm like, you could use the quick formula that we just learned, or you could do Pythagorean theorem from the base foundation and be fine. If you calculate that, that's 49 plus 16, that's 65, which is nothing good. So R equals the square root of 65. Feeling good?
Really, so for the one that's the square root of x squared plus y squared, that's to find a radius.
Yeah.
But for the one that's tan cos, do those find like the one that's the equation kind of thing?
That would find x values and y values. We'll do a different question. We have to do that.
Okay.
We don't have to do that now, so don't worry about it. B. Oh, sorry. This radius. It's the square root of 65. You always want to use exact values. You always want to use simplified values. Right? Square root of 65 can't be simplified. But if it could be, you would. Right? That makes sense? So if it was square root of 8, then I would have simplified it to be 2 root 2. Alright. Determine the 3 primary trigonomic ratios. The trigonomic ratios are SOHCAHTOA. So that means they want you to find sine of theta equals opposite over hypotenuse. I'm going to write out all 3. Cos of theta equals I thought I could squeak it in, but I know I can't. Cos of theta equals adjacent over hypotenuse. Tan of theta that's what I'm going to need the least amount of space for. Equals opposite over hypotenuse. Okay, we're going to write out the trigonomic ratios for these things. Those are the 3 trigonomic ratio formulas. The ratio for sine is opposite over hypotenuse. So if you're trying to find the actual ratio for this question, the ratio would be 7 divided by root 65. Right? That's opposite over hypotenuse. So when they say find the trigonomic ratio for sine of theta, the answer is 7 over root 65. Everybody's good up to that point? So I'm about to make it worse for you. Why is that not the right answer on a test? It's not simplified in the sense that there's a square root on the bottom. Unit 1, right? No square roots are allowed on the bottom. So that means you need to rationalize your denominator. So to rationalize a denominator, you multiply the top and the bottom by root 65. That makes your final answer 7 root 65. I told you I tried to squeeze it. I'm going to do this next. 7 root 65 over 65. That's how it would look. That would be your answer. That's your sine ratio. That means your cosine ratio would be adjacent over hypotenuse. Adjacent being 4, hypotenuse being root 65. You need to rationalize that denominator, multiply top and bottom by root 65, making it 4 root 65 over root 6. Oh, sorry, just 65. Got rid of the root. That's small writing, so feel free to ask what numbers those are. It was 4 over root 65. I rationalized it. It became 4 root 65 over 65. Tangent's going to be the easiest one because there's going to be no rationalizing. So if you wanted to solve the tangent ratio, that means you're looking for opposite divided by adjacent. That would be 7 over 4. So that one's the easiest. Any questions on that? All right. Asking for the ratio is very different than asking for the angle. So look at the question B and question C. Those mean different things. The ratios are those three fractions I just calculated. And when I ask you for a ratio on a test, I'm not asking you to calculate the angle. I'm not asking you to turn that into a decimal. All I want is that fraction. I'll probably ask you in the next step, what's the actual measure of the angle? To find the measure of an angle is when you do second sine or second cos or second tan. In this case, since I know all three ratios, all three of them would give me the same answer. So I'm just going to do 10 because 7 over 4 is the easiest numbers. So I'm going to go tan, -1, 7 over 4. If I put that in my calculator, what's my standard position angle equals under? 60 degrees? And you could do that with any of the ratios and get 60 degrees. So I could do sine, I could do cos, I could do tan, they all give me 60 degrees. Alright, there's a practice problem there for you to try on your own. It's the exact same, so try it maybe later for homework. It's a good idea. We're going to do this one. If we have time, we'll go back and do the practice together. The reason we're going to do this one is because it shows you why knowing the ratios are useful. This is a guaranteed question on a test. It says the angle theta is in standard position in quadrant 1. Tan of theta equals 2 over 7. What are sine of theta and cos of theta? They're not asking you for what theta is. They're asking you for the sine ratio and the cos ratio. That's what they're asking you for. Sine of theta equals opposite over hypotenuse, right? Cos of theta equals adjacent over hypotenuse. They're asking you for those values. They're asking you for the fraction. What does tan of theta tell you?
The opposite.
Yeah, it also tells you opposite and adjacent, right? You're both right. This is telling you two sides of a triangle. But now those opposite and adjacent mean something. They mean x and y. Just like the formula we created a few slides ago, tan of theta equals x over y. They're telling you the points of your terminal arcs. Tan of theta told you you have a point at 2, 7. Now you can build a triangle. Where's theta in this triangle? Standard position. Theta's right there. Yeah. Thank you. Opposite over adjacent is simply y over x. I got so excited. And that's like the formula that we talked about. So that is, oh, here we are. My apologies. That makes our triangle like this, which would be, I almost did it again, 7, 2. Thank you. That's how trig is going to work in this unit. So they're going to give you a ratio. When they're giving you a ratio, they're actually giving you sides to something. If I give you the sine ratio, then I would have been giving you the r, and I would have been giving you the y. If I give you the cos ratio, I would have been giving you the r and the x. As long as it's in standard position. Right? That's why they use that term. That's why they actually said it in there. Yeah.
If you're using sine or cos, do you know where to put your point?
That's a really good question, and we do that tomorrow because it depends on this piece of information, which is actually very important to us. We just didn't know it was important because we've always been in quadrant 1. But tomorrow or Thursday, it'll become important. All right, from this point on, if I want to find the sine ratio, I need the opposite, which is going to be 2, divided by the hypotenuse. What's the hypotenuse? We don't know. We call it r. How could you find the hypotenuse? Use Pythagorean theorem, or use your new formula for r, which is x squared plus y squared, and then square root. That's 49 plus 4, that's square root of 54.
53.
Thank you. Woo! What's going on?
That grade 9 math.
Grade 9 math, right? What we just talked about. Yeah. So now you can actually find the ratios, right? Because you know what this side is. So when they say, what's the sine ratio? Your answer would be 2 divided by root 53. If they asked you what the cos ratio would be, it would be 7 over root 53. Ratios are telling you side lengths. They're telling you either r, x, or y, 2 of the 3 every time. Very useful. Those formulas, remember the ones we made together? That's how you can do questions quick. Because you'll already know the formula. You don't need to do the SOHCAHTOA and the rearranging. But you always could if you needed to. You could always go right back to basics, which is sometimes useful because it gives you like an emergency plan out of almost every question. All right, those answers are really nice. They're both wrong. You got to rationalize both of them, right? So if this was a test, you would get to 2 root 53, you'd look at all your answers and they wouldn't look anything like that. And you'd be like, what the heck is going on? Remember to rationalize your denominators. That would be multiply the top and the bottom by root 53. When you do that, that turns the sine ratio into 2 root 53 over 53. And it turns the cos ratio into 7 root 53 over 53. Those would be your final answers. If that's a test, a written question, you probably get half mark. If you left it to. You get the other half mark by probably rationalizing. That's probably about what you'd lose for not rationalizing. Half mark. Okay, there's another one of these. I want you to try to set it up. Okay? So actually, I'll give you 3 minutes to do as much as you can, and then I'll rip through it. Okay, so try your absolute best. They want to know what the sine ratio and the tangent ratio are. They're not asking for the actual measure of theta. If you're looking at this question, 5 over 13 gave you 2 things. It gave you your x value, and it gave you your r value. That lets you set up your triangle. You then use Pythagorean theorem to find your other side. And once you have that side of 12, you can set up your other ratios, which are just using standard Pythagorean theorem. Awesome. Thank you.